Welcome everyone. In this talk, I want to walk you through the journey from sensing to actuation in autonomous transport systems. When we say autonomous transport system, we mean any vehicle that can perceive its surroundings, interpret what it sees, make decisions, and then move safely without continuous human control. That can be a car, a shuttle, a mobile robot in a factory, or even an automated tram. My focus today is not on a single algorithm, but on the overall architecture that links sensors to intelligent decisions and finally to the actuators that steer, brake, and accelerate the vehicle. We will see how each layer, sensing, localization, and mapping, decision-making, and control, depends on the others. Modern autonomous driving stacks follow a similar structure: perception, prediction, and planning, control. By the end of the lecture, you should have a clear picture of how information flows through this pipeline and where your future work could contribute. This slide gives you the roadmap for the lecture. We start with Module 1, Sensors, the perception layer. Here we look at cameras, LiDAR, radar, encoders, and we discuss noise, uncertainty, and basic ideas of sensor fusion. These are the eyes and ears of the system. In Module 2, we move to localization and mapping. Once we have sensor data, the vehicle must answer, where am I and what does the world around me look like? This is where SLAM and map representations come in. Module 3 covers the Führungsarchitektur, the decision layer. Here, global and local planners, prediction modules, and behavior decision work together to generate safe, comfortable trajectories. Finally, Module 4 focuses on Actuation and control. We translate planned trajectories into physical motion using vehicle models and controllers such as PID and model predictive control. Think of this roadmap as 4 layers stacked on top of each other: sensors at the bottom, then localization and mapping, then decision-making, and on top of that, the control that actually drives the vehicle. We begin with Block A, sensors, the perception input layer. Autonomous vehicles need 2 categories of sensors. First, proprioceptive sensors measure the state of the vehicle itself: wheel encoders, IMUs, wheel speed sensors, and sometimes motor current sensors. They tell us how the vehicle is moving, its speed, acceleration, and orientation. Second, exteroceptive sensors look outward at the environment: LiDAR, cameras, radar, ultrasonic sensors, and GNSS. They detect other cars, pedestrians, free space, lane markings, and obstacles. None of these sensors is perfect. Each gives a partial, noisy, and biased view of reality. Cameras struggle at night or in fog. LiDAR is affected by heavy rain. Radar has lower spatial resolution. Because of this, higher layers must always treat sensor readings as uncertain and combine multiple sources. And keep in mind, please, that sensors form the foundation of all later reasoning. But if perception is wrong, even the best planner or controller cannot save the system. Now we take a closer look at one important exteroceptive sensor: LiDAR, light detection and ranging. A LiDAR unit emits short laser pulses and measures how long they need to come back after bouncing off objects. Using the time of flight, it computes very accurate distances. By rotating or using multiple beams, the sensor builds a 3D point cloud of the surroundings. So we see how LiDAR scans the environment and creates a dense 3D model of buildings, cars, and pedestrians around the vehicle. Every dot in that cloud is one measured distance. Why is this powerful? Because it gives us precise geometry: where obstacles are, how high they are, and how far away. This makes LiDAR very attractive for mapping, localization, and obstacle detection, especially in complex urban environments. Now we take a closer look at one important exteroceptive sensor: LiDAR, light detection and ranging. A LiDAR unit emits short laser pulses and measures how long they need to come back after bouncing off objects. Using the time of flight, it computes very accurate distances. By rotating or using multiple beams, the sensor builds a 3D point cloud of the surroundings. In the video linked on this slide, you see how LiDAR scans the environment and creates a dense 3D model of buildings, cars, and pedestrians around the vehicle. Every dot in that cloud is one measured distance. Why is this powerful? Because it gives us precise geometry: where obstacles are, how high they are, and how far away. This makes LiDAR very attractive for mapping, localization, and obstacle detection, especially in complex urban environments. On this slide, we stay with LiDAR but talk more about its strengths and weaknesses. The big advantages are very high distance accuracy and angular resolution. Works well in low light or at night because it does not depend on sunlight or street lights. Produces data that is naturally compatible with mapping and SLAM algorithms, but there are also clear limitations. LiDAR units are still relatively expensive compared to cameras or radar. Performance can degrade in rain, fog, or snow when laser beams are scattered. A point cloud contains geometry but very little semantic information. It is harder to know if an object is a car, a pedestrian, or a sign. In practice, LiDAR is rarely used alone. It is combined with cameras and radar so that we benefit from its precise 3D geometry while other sensors provide semantics and robustness in bad weather. On this slide, we focus on radar and compare it to LiDAR and cameras. Radar stands for radio detection and ranging. It sends out radio waves and measures the reflected signals. From these reflections, it can estimate distance and relative velocity of objects using the Doppler effect. The big strengths of radar are it works very well in bad weather. Rain, fog, dust, and snow affect radio waves much less than light, so radar keeps working when cameras and LiDAR start to struggle. It has long range, which is valuable on highways to detect vehicles hundreds of meters ahead. It measures velocity directly, which helps with tracking moving targets and collision warnings. It is relatively low-cost and mature technology, already widely used in automotive ADAS such as adaptive cruise control and emergency braking. But radar also has clear limitations compared to LiDAR and cameras. Its spatial resolution is low, the point cloud is sparse and blurry, so it is difficult to separate small or closely spaced objects. It provides almost no appearance information, no color, no texture, and only rough shape, which makes object classification much harder than with cameras. Radar returns can contain clutter and multipath reflections, which need careful signal processing and learning-based methods to clean up. Compared to LiDAR, radar is less precise in geometry but more robust to weather. Compared to cameras, radar has much poorer detail but gives reliable distance and speed. The key message here is that the radar is the weather-robust, long-range velocity expert, but it needs LiDAR and cameras to provide high-resolution geometry and rich semantics. This slide focuses on cameras and how they compare to LiDAR and radar. Cameras are passive optical sensors. They capture reflected light and produce 2D images just like a human eye, but with a digital sensor. Their main strengths are extremely high resolution, millions of pixels, which makes them ideal for detecting fine details such as lane markings, traffic signs, traffic lights, pedestrians, and object shapes. They provide rich semantic information, color, texture, and context, which deep learning models can use for object detection and scene understanding. Cameras are cheap and widely available, benefiting from the smartphone and consumer electronics industries. This makes large-scale deployment and redundancy economically feasible. However, cameras also have important limitations. They do not measure depth directly. Distance must be inferred through stereo vision, motion cues, or learning-based depth estimation, which is less reliable than LiDAR range measurements. Their performance depends strongly on lighting conditions. Low light, glare, shadows, or overexposure can dramatically reduce reliability. They are sensitive to weather. Heavy rain, fog, and snow degrade contrast and may cover the lens. In comparison, LiDAR provides accurate 3D distance information almost independent of ambient light, and radar provides robust range and velocity even in bad weather. Cameras, in contrast, are the best at understanding what an object is and what the scene means. We conclude that the cameras are the semantic experts of the sensor suite. They understand signs, lanes, colors, and object types, but they must be combined with LiDAR and radar to get dependable depth and robustness in all conditions. This slide answers a crucial question. Why do autonomous systems need probability theory? Every sensor measurement is imperfect. Cameras introduce noise, LiDAR points may be missing, radar has clutter and multipath, and IMUs drift over time. On top of that, the environment itself changes. Lighting, weather, and surface properties all affect the readings. If the robot treated each measurement as a 100% reliable fact, it would constantly make wrong decisions. Instead, we model each quantity, position, velocity, distance as a probability distribution. This is exactly what filters such as the Kalman filter and its variants do. They combine predictions from the motion model with noisy sensor observations to produce a best estimate with uncertainty. The key idea here is that an autonomous vehicle never knows the truth, it estimates it and always keeps track of how uncertain it is. This probabilistic mindset is the basis for safe decision making. Now that we accept that raw sensor data is messy, this slide shows the processing pipeline that turns it into something useful. First, we apply filtering, denoising images, smoothing LiDAR points, removing outliers in radar. This reduces random errors. Next, segmentation groups pixels or points into meaningful regions. For example, road surface, sidewalk, cars, pedestrians, free space. This can be done with classical methods or with deep learning. Then we perform feature extraction. We compute edges, corners, key points, shapes, or learned features from neural networks. These features are more compact and informative than raw measurements. Object recognition uses those features to detect and classify objects. This is a car, this is a cyclist, this is a traffic sign. Finally, sensor fusion combines information from multiple sensors. For example, camera plus LiDAR plus radar to get a more robust and accurate view of the world. After these steps, the data is no longer just numbers. It is a structured description of the environment that can be used by planners and controllers. With perception in place, we move to the control architecture, often called the brain of the autonomous system. The basic flow is localization and state estimation provide the best estimate of where the vehicle is and how it is moving. Mapping and environment understanding maintain a representation of the world, static elements like roads and buildings, and dynamic objects such as other vehicles and pedestrians. Global planning computes long-range routes, for example, from one city block to another. Local planning focuses on the next few seconds, finding collision-free trajectories that respect road rules and comfort. Behavior and decision modules choose maneuvers such as lane changes, yielding, or overtaking. Safety monitors supervise everything and can trigger emergency braking or safe stop if something looks wrong. All these components must work together in real time, under uncertainty, and with strict safety requirements. This slide zooms into localization. The vehicle constantly asks, "Where am I right now?" To answer this, it combines prediction and correction. Prediction comes from motion sensors and models. Wheel odometry, steering angle, and the IMU tell us how the vehicle has moved since the last step. Using a kinematic or dynamic model, we can predict the new pose, position, and orientation. Correction uses measurements from the environment, visual landmarks from cameras, LiDAR scan matching against a map, or radar reflections from known objects. These observations pull the estimated pose back toward reality and limit the drift that pure odometry would accumulate. Modern localization systems fuse these signals probabilistically to obtain a pose estimate with bounded error. Without a stable localization, planning and control simply cannot work. Here we revisit the control architecture now that localization is clear. You can think of the architecture as a pipeline. Localization and state estimation give us a reliable pose and velocity. Mapping and environment understanding build a world model, often called a virtual world, around the vehicle. On top of this world model, global and local planners search for safe, feasible trajectories that bring the vehicle closer to its goal while avoiding obstacles and respecting traffic rules. This slide reminds us that we are moving upward in the stack from "where am I" to "where should I go next and how do I get there safely?" In many real environments, we do not have a perfect map in advance. That is where SLAM, simultaneous localization and mapping, comes in. SLAM tackles two problems at the same time: localization, estimating the pose of the vehicle, mapping, building, or updating a map of the environment. As the vehicle moves, it collects sensor data, LiDAR scans, camera images, radar returns, and incrementally adds new landmarks or obstacles to the map. At the same time, it uses those same observations to correct its own pose. Modern SLAM systems rely on feature extraction, scan alignment, and graph-based optimization. They also include loop closure. When the vehicle revisits a known place, the system recognizes it and corrects accumulated drift in the map. For autonomous transport, SLAM is essential when operating in changing or previously unmapped areas, such as new construction zones or indoor logistics environments. We return once more to the control architecture, now with planning in place. At this level, global planning provides a course route, local planning generates a short horizon trajectory that avoids obstacles, and behavior modules decide maneuvers such as following, stopping, or lane changes. The output of these layers is not just a destination, but a time-parameterized trajectory, a sequence of positions, velocities, and headings that the vehicle should follow over the next few seconds. The next step is to turn this desired motion into concrete commands, steering angles, throttle, and braking, under the physical limitations of the vehicle. That is the topic of the next slide on actuation. Actuation is where software meets physics. The goal is to track the planned trajectory as closely as possible while keeping the vehicle stable and comfortable. To do this, we need kinematic and dynamic models that describe how steering and acceleration change the vehicle's motion, controllers such as PID, nonlinear controllers, or model predictive control. PID is simple and widely used. MPC can explicitly consider constraints like maximum steering angle or tire forces. Actuators, steering motors, brake systems, and powertrain that execute these commands. Feedback loops using IMUs and encoders to measure what actually happened and correct errors. If this layer fails, even a perfect planner cannot guarantee safety, so motion control is both a control theory problem and a safety-critical engineering task. His slide emphasizes that safety and reliability are non-negotiable in autonomous systems. We use redundancy, multiple sensors, multiple communication paths, sometimes even multiple computing units, so that the system can tolerate individual failures. Fault tolerance means the system does not immediately collapse when something breaks. For example, losing one camera should not cause a crash. The vehicle should fall back to LiDAR and radar. Safety protocols include safe stop behaviors, emergency braking, and clear limits on when the system is allowed to operate. Finally, we need extensive testing, verification and validation, from simulation to test tracks to controlled on-road trials. This ensures that the vehicle behaves safely not only in nominal conditions, but also in rare corner cases. An autonomous system is not just clever, it must be trustworthy. Looking ahead, several technological trends are reshaping control architectures. AI and machine learning are being integrated more deeply into perception, prediction, and even control, for example, through deep reinforcement learning for decision-making and trajectory planning. Advanced sensors, including higher resolution LiDAR, imaging radar, thermal cameras, and event-based cameras, provide richer and more diverse data streams. There is growing interest in neuromorphic computing and edge AI, where hardware mimics aspects of the human brain to process sensory information with very low latency and power consumption. Together, these technologies aim to create autonomous systems that are not only more capable, but also more robust in edge cases, easier to update over the air, and better integrated into broader mobility ecosystems.
Let me close by summarizing the key points. We have followed the path from sensing to actuation. Sensors provide noisy, partial information about the environment and the vehicle itself. Through probabilistic modeling, filtering, segmentation, feature extraction, object recognition, and sensor fusion, we convert raw measurements into a structured understanding of the world. On top of this, the control architecture, localization, mapping, planning, and decision-making generates trajectories that satisfy safety, comfort, and efficiency goals. Finally, the control and actuation layer, turns those trajectories into actual motion under the constraints of vehicle dynamics and safety requirements. Different architectures may vary in detail, but they all share this basic flow, and across all layers, safety and reliability remain the central challenges.
I hope this lecture has given you a clear, structured view of how autonomous transport systems are built, and maybe also some inspiration for where you could contribute, whether in sensing, AI, planning, or control.